All right, in example 1, we have f of x is equal to x cubed minus 3x. We want to know, where does this function f have horizontal tangent lines? So if you just look at the graph, at what x values do you see horizontal tangent lines? 1, and here it is right down here, and at -1. Right. Okay. It's these locations of the horizontal tangent line that's going to tell us lots of information about how to break up the function and where to look for things in the function. So for what x values? X equals -1 and x equals +1. And then the question is, how would you describe the graph at these points? We're going to use words like local min and local max. Now, your book is more in favor of using the term relative min or relative max. Local and relative mean the same thing. Okay? So if you see local or you see relative, those are all the same. Now, in what respect is this a maximum? Okay? Notice that this point right here, this is the highest and largest value that the function takes on, but only in that little section. Okay? Clearly, there are other points over here. As we go further, this will go to infinity. There are other points that are going to have a larger value, but only in this little section over here, the one point when x is equal to -1, is this function the highest. Same thing down here. When x is equal to +1, this is the smallest that the function gets in this little neighborhood. Okay? It is with that respect that we say that it is a local minimum or a local maximum. Okay? And when we get to chapter 6, we will be doing what we call absolute maximum, which is the biggest, period, and absolute minimum, which is the smallest, period. Okay? But today, it's all about the locals. Consider the derivative, f of x, f prime of x. The derivative of f tells us the blank of the graph of f at each point. So what does the derivative tell us about the graph? One word. Slope. Okay? So the derivative is used to tell us the slope. Now, in the bullet points, f prime is greater than 0. So think about the scenario. If f prime is the slope, what do we know about a function that has a positive slope? What is the function doing at that point? It is increasing. So a positive slope on a function means that that function is increasing. If f prime is less than 0, in other words, if f prime is negative at some point, then what is the graph doing at that point? It is decreasing. And if f prime is 0 at some point, then the graph has a horizontal tangent line at that point. To be constant, you would have to be constant on a sort of a series of points, but yeah, and this one is in particular at a certain point. But we could get to that as well. All right, so these three, and in particular these upper two, this is the key to doing today's lesson. Knowing when the derivative is positive, that means the function is increasing. Knowing where the derivative is negative means the function is decreasing. Let's look at example 2. It's the same equation from the top. F of x is equal to x cubed minus 3x. First, we want to find f prime. Then we're going to create this sign chart that you see here and determine where f prime is positive, f prime is 0, and f prime is negative. We will use that information to state whether the function is increasing, where it is increasing, and where it is decreasing. Okay? Now, I should mention that there are two types of sign charts. This is the one that I've created that's sort of a box. It condenses all of the information that you're going to need to make these determinations. There are the other ones that you could use where it's just the number line and you put things on top of the number line. You will see that sometimes as well. Okay? So, and we already know the answer to this problem because we know what the graph is from the top of the page. But let's show you how to work it algebraically and with calculus. So the first thing we want is the derivative. So the derivative of x cubed minus 3x is 3x squared minus 3. Now, we've already done some work with sign charts and information about that. we know that this function, that is the derivative, is polynomial. The only place polynomials can change signs is when they pass through their zeros. So we naturally set this equal to 0 and solve for x. I'm going to factor out 3. And then x squared minus 1 factors. And we get x equals 1, x equals negative 1. And if we try to set 3 equal to 0, we don't get any solution from that. So that's just nothing there. And here it is. Here's the 1 and the negative 1 that you told me from above. Now we're going to use this information to create the sign chart, create the intervals, and determine where the function is increasing and decreasing. The sign chart, that's the box version that I have here on the left, has 4 rows. In the top row, it's the points that we got from finding this solution on the right, then the intervals, then the sign of the derivative, and then whether the function is increasing or decreasing based on that information. Notice that these bars, they don't go all the way to the top. In fact, the numbers sit atop those bars. These are actually called partition points. The x equal 1 and the x equals negative 1, those are our 2 partition points that we're going to put into the table. In addition, the table has to be organized increasing from left to right. So the negative 1 goes on the left and the positive 1 goes on the right. From that, you are going to take the domain of the function, which, since this is polynomial, is everything, and you're going to split it up into intervals with negative 1 and positive 1 as partition points. So we get negative infinity to negative 1, negative 1 to 1, and 1 to infinity. Next, we choose test points in each of these intervals, and we test it in the derivative. That will determine if every point in each of the intervals is positive or negative. Because remember, the derivative can only change signs at these partition points, negative 1 and positive 1. So if I test any point within the interval that's created, they all have that same sign. They can't change anyplace else. So f prime of, and I'm going to pick from this first interval, I'm going to pick negative 2. Now let me show you a neat little trick here. It's actually easiest to pick some factored version of the derivative to test these things in, because you do not care what the value is. You only care about what the sign is. Okay? So if I pick negative 2, this would be 3 times negative 2 minus 1 times negative 2 plus 1. And at this point, all I want to know is what the signs are. So 3 is positive, negative 2 minus 1 is negative, and negative 2 plus 1 is positive or negative? That is negative. And so I have positive times negative, resulting in a positive. That is a positive. And from the chart above, if the derivative is positive, then the function is increasing. To denote increasing, we use a slanted upward to the right arrow. We are reserving the straight up and down arrow for something on Wednesday. Okay, so that will have another meaning. Okay, so we have to use a slanted one here. All right, if I continue on and test points in these intervals, from the interval negative 1, 1, I'm going to test f prime at 0. So it's going to be 3 times 0 minus 1 times 0 plus 1. That is equal to a positive times a negative times a positive. That is a negative. And that means we are decreasing. And the last one I would test is at positive 2. So we have 3 times 2 minus 1, 2 plus 1, which is positive, 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 resulting in a positive, which is increasing. The final piece here is to make a statement. The statement is f is increasing on, and then you give me the interval that it's increasing on or the union of such intervals. So it would be increasing on negative infinity to negative 1, union 1 to infinity. F is decreasing on negative 1 to 1. All right, example 3, f of x is equal to 4x minus x to the fourth. We want to know where this is increasing or decreasing. So we'll go again, we find the derivative. And the derivative would be 4 minus 4x cubed. We have a polynomial, so we want to know what its zeros are. So we set it equal to 0. Now this one you could do one of two ways. You could end up factoring it, and you'll have the difference of cubes, and you're welcome to do that. When you do factor it with the difference of cubes, and it started out as x cubed, the linear part will give you the solution. The quadratic part will not. Okay, so you will only get one solution. Because we know this for a fact, we can actually just solve it this way, and we will get the one solution. And we get x equals 1. Okay. Now, we're going to draw the box. So we have points. Now this time, we only have one partition point. So it's a 1, and we draw the line straight down under it. So the number of sections in your box is dependent on the number of partition points you end up with. The intervals would be negative infinity to 1 and 1 to infinity. I need to test f prime, so I'm going to test it first at 0. So this will be 4 minus 4 times 0 cubed, which is a positive. And I'm going to test it at 2. Be 4 minus 4 times 2 cubed, and that clearly is going to be negative. Based on the signs of the derivative, we know where the function is increasing, which is on this first interval, and decreasing on this second interval. So then we make a statement. F is increasing on negative infinity to 1. F is decreasing on 1 to infinity. Okay. So we now have the definition of critical value. And you're going to see some other terms as well. You have critical value, and you have critical number, and you also have critical point. Critical value and critical number are the x values. Critical point is a point. So that's how you know. So the definition of critical value is values of x in the domain of f where f prime of x is equal to 0 or f prime of x is undefined. Okay, these two conditions. If you have one of these conditions, then you create your critical values. So now the numbers that go in as the partition points are these critical values, and it also has to be representative of the original domain. Okay. Let's take a look at example 4 where we find the critical values. So find the critical values of f of x is equal to x to the fifth plus 3x to the fourth minus 3x cubed. So to find the critical values, I need to do these two things. I need to find where the derivative is 0, and I need to find where the derivative is undefined. So first I'm going to take the derivative. You get 5x to the fourth plus 12x cubed minus 9x squared. Okay. What type of function is the derivative? What is it? It is polynomial. Polynomial functions are continuous and defined where? Everywhere. So this, since it's polynomial, is never undefined. Okay? So f prime is never undefined. So we get no contribution from this second part of the definition of critical value. So all we do is we rely on the first part where it's equal to 0, and then we just solve for x. Okay? So if we need to solve where the derivative is equal to 0, well, we're going to factor out by x squared. That leaves 5x squared plus 12x minus 9. Then we check to see if this is going to factor, and sure enough, we get 5x and x, 3 and 3. If I take the product of the outers, I get 15. The inners would be 3, and so since it's positive 12, I need the 15 to be positive, and the inner 3 to be negative. Set each factor equal to 0. If I set x squared equal to 0, I do in fact get x equals 0. This is the other example, the different example from if you had just a number in front. Numbers in front do not give you any extra solutions. An x in front does. X squared equals 0 gives you x equals 0. If I set 5x minus 3 equal to 0, what do I get? I get 3/5. And x plus 3 equals 0 gives me x equals negative 3. So I, in fact, do have 3 critical values here. Example 5. Find the critical values of f of x equals the square root of x. So we'll start by taking the derivative. What is the derivative of the square root function? 1 over 2 square roots of x. So we need to do the two pieces here. We need to take the derivative and set it equal to 0. And we need to take the derivative and find where it is undefined. Okay, so we'll do these in two pieces. In the first half, we're going to set the derivative equal to 0. And remember, when you have a rational function, well, this is not rational, but at least it's a fraction. When you have a fraction with x's and it's equal to 0, that's the same thing as setting the numerator equal to 0. You get 1 equals 0, which is not true. So nothing here, right? But maybe we get something on the right side. Okay, so no critical values were gained from setting the derivative equal to 0. Now we're going to find where the derivative is undefined. To find where a fraction is undefined, you set the denominator equal to 0. So if I solve for this, divide by 2, square both sides, I get x is equal to 0. Now, this may or may not be a critical value. We have one more thing to verify. And the question is x equals 0 in the domain of the original f? In order to be a critical value, you have to be in the domain of the original function to start with. So, can you find the square root of 0? Yes. Square root of 0 is 0. And so it is in the original domain. So this is, in fact, a critical value. So yes, and so this is a critical value. So that's an example of a function where you only get critical values from f prime being undefined. not from it being equal to 0 itself. Local extrema, first thing you need to know is that extrema is actually the plural of the word extremum. Okay? And there's lots of words in science and math where we take a word that ends in um and make it plural by changing that to an a. Your favorite example is bacteria. You have 2 bacteria, you have 1 bacterium, right? The old school ones that we don't use anymore is 1 stadium and 2 stadia. They got rid of that one and they just say stadiums now. But in the old days it was stadia. Yeah. But also a stadium was a unit of measure. It was a distance. So stadia and things. And we're going to use this with other words as well. Maximum, maxima, minimum, minima, optimum, optima, things like that. Okay? So, your local extrema refer to both the local minimum, which looks like this. All right, it's that point down here at the bottom. Or a local maximum, which looks like this. Local extrema occur only at critical values. But not all critical values result in extrema. Okay? So if you're going to have an extreme value, it has to occur at a critical value. But just because you have a critical value, that doesn't mean you're going to get an extreme value. It doesn't quite work that way. The canonical example of such a thing is the following. Example 6. Show that f of x equal to x cubed has a critical value, but no extreme values. Okay? So if it's an extreme value, it would be a local min or a local max. Here is the graph of the cube function. You know it well. Looks like this. Is there any place where there is a local minimum? No. Is there any place where there is a local maximum? No. In fact, it is increasing and it just keeps going. It just keeps increasing throughout its whole domain. Now let's show that with calculus. So the first thing we want to do is find all the critical values. Critical values come from the derivative either being equal to 0 or where the derivative is undefined. This one is going to be 3x squared. That's polynomial, so it's never undefined, so we don't have to worry about that part. But then it is set equal to 0, and we get a solution of x equals 0. From here, we can create the chart of 0. The intervals would be negative infinity to 0, 0 to infinity. Okay. If you test f prime, in fact, you can look at this piece right here. What do we know about x squared? X squared is always positive or 0. Well, we have found every place where it's a 0, so that means at every other place it must just be positive. Well, all those other places are these intervals that we've created. So f prime is always positive, which means that f is always increasing on both sides, which means there's no place for it to have a local minimum or a local maximum. In order to have a local max, it would have to be increasing followed by decreasing. To have a local minimum, it would have to be decreasing followed by increasing. Okay. So we have a critical value, but no extremum. In example 7, find the extrema of f of x is equal to x cubed minus 9x squared plus 24x minus 14. So we need to take the derivative. It's going to be 3x squared minus 18x plus 24. To find the extrema, we need the critical values. This is polynomial, so it doesn't have any critical values from being undefined. So we will set it equal to 0. Factor out the 3. And we get x squared minus 6x plus 8. Then we're going to factor x squared minus 6x plus 8. And we get x minus 2 and x minus 4. And you would set each of these equal to 0. So 3 equals 0 is no solution. X equals 0, x minus 2 equals 0 is x equals 2. And then x minus 4 equals 0 is x equals 4. So we have these two critical values. We'll use these critical values in the sign chart table. Since we have two critical values, we make two partitions, and that gives us 3 intervals. Again, I think it's easiest to use the factored version of the derivative to determine the signs of the derivative, but you're welcome to use any version you'd like. We just have to pick up on some points. So f of 0 would be 3 times 0 minus 2 times 0 minus 4, and that would be positive. I'm going to pick up f prime of 3. This would be 3 times 3 minus 2 and 3 minus 4. I have positive, positive, negative, so that's a negative. And then f prime of 5. It's 3 times 3 minus, should be 5. 5 minus 2, and then 5 minus 4. Positive, positive, positive gives a positive. So it tells me we're increasing, decreasing, increasing. Now we want to identify the extreme types and their values. So when the book asks for the extreme value, that is the y value. Okay, so we'll have to figure that out on the calculator. But first, let's identify what type of points we have. At coming into where x is equal to 2, we have increasing followed by decreasing. What type of extreme value is that? That is the local max. And then coming into 4, we have decreasing followed by increasing.
Minimum.
That is a minimum. Yeah. Okay. So to find the extreme values, we would plug in 2 in the original. Okay. So make sure your notation is right. This is not the derivative. This is the original value. And I will just whip that out on the calculator. 2 squared. That is a value of 6. So that is the local maximum. And then we want f of 4. Again, we're plugging these into the original. And then actually that's a 2. And that's a local minimum.
2 and the 4 weren't in the local maximum?
A local maximum and a local minimum are points. So the point here is 2, 6, and the point here is 4, 2. So use the x and the y. Let me draw the graph for you. So what type of equation is the original function? What type of polynomial? It is a cubic polynomial. You know that cubic polynomials have opposite in behavior. Okay? The lead coefficient is positive, so we know it's going to start down and it's going to end up somewhere. Using this information about the local extrema, we can now dictate the curves on the inside. When we get to x equals 2, it's going to go up to 6, and when we get to 4, it's going to come down to 2. Right there. So there and there. It has some roots. We can't figure those out with the information given, so we're just going to assume it does something like this. So that's a local max, and that's a local min, and then it does something like that. That's a rough sketch, okay? We could have done a better job with the y-intercept, but that's all right. I wanted you to see how it bends around these extrema, okay? Find all extrema of f of x is equal to 1 minus x raised to the 4/5 plus 3. So the first thing we need to do is find what? Find the derivative. Okay, we've got a power function here. So we're going to bring the 4/5 to the front, times the inside unchanged, lower the power by 1, and what's the new power? Negative 1/5, times the derivative of the inside. The inside is pretty trivial. It's x minus 1, so the derivative of that is 1. Nothing new to gain there, but you still need to think about it. Think about the chain rule all the time. And then the derivative of 3 is 0, so that's the end of that. So we can rewrite this. 4 on top, 5 on the bottom. The x minus 1 is being raised to a negative exponent, so that sends that to the bottom as well with a positive exponent.
Wait, what happened? What did that happen?
The exponent was negative, so it went to the bottom. All right. We need to find the critical values. There are 2 ways to find critical values. Set the derivative equal to 0. If we were to set f prime of x equal to 0, that would result in the numerator being equal to 0, which is no solution. So nothing to gain there. Okay. On the other side of this, we need to set the denominator equal to 0 to find where f prime is undefined. So this would be 5 times x minus 1 to the 1/5 is equal to 0.
So is it still positive?
It's still positive because we're taking the denominator as a whole. All right, to solve for x, we need to work our way inside the parentheses. We get rid of the 5 first, so divide both sides by 5. 0 divided by 5 is still 0. To get rid of the 1/5 power, I'm going to raise both sides of the equation to the 5th power. That, in turn, cancels off these powers, right? It essentially makes them 1, right? That leaves me with x minus 1 equals still 0. So x is equal to 1. Now, this would be a critical value if 1 is in the original domain. So you've got to go back to the original function and see if 1 is in the original domain. Can you plug in a 1 into this function? 1 minus 1 is 0. Can you raise 0 to the 4/5 power? Yes. And you get 0. And then 3 is 3. So it does work. So you can do that. So you can do 1 minus 1 to the 4/5 plus 3 is 0 to the 4/5 plus 3, which is 0 plus 3, which is 3. So as long as all those calculations work out, then the 1 was in the domain. So this one is in the domain, and it is a critical value. Next, we create the table. Do you want me to do the table, or you want me to do the line chart, the line graph? Okay, let's do the table. All right. Now you have to think about the domain of the entire function as well in order to figure out what these intervals are. What does this 5 right here mean in the bottom? That is the 5th root, okay? Right? So this is what you have to worry about. You have to worry about what root you're taking. If you are taking an odd root, 5th root, 3rd root, 7th root, 9th root, you can take that of both positives, negatives, and 0. It's the even roots that you have to be careful of. You cannot take the even root of negative numbers. Right? Those are what ends up being imaginary numbers. Okay? So the square root of negatives is out. 4th root of negatives, gone. Right? But the 5th root, everything is fair game. So we're going to put the 1 in the box here. And the domain of this original function is everybody. Right? So this is going to go from negative infinity to 1, and then 1 to infinity. F prime, and then F. And we need to do some testing. And we need to test the derivative. I'm going to test it in this form right here. So f prime of 0 would be 4 over 5 times 0 minus 1 to the 1/3, 1/5 rather. Okay. The denominator is negative 1 to the 1/5. Okay. You are taking the odd root of an odd number. That results in an, sorry, not odd, negatives. You are taking the odd root of a negative number. That results in a negative. Okay. So it's positive divided by a positive times a negative, which is going to be a negative. And then f prime of, let's say, 2 would be 4 over 5 times 2 minus 1 to the 1/5. This is going to be a positive divided by a positive. 2 minus 1 is 1. 1 to the 1/5 power is positive. And so this is all positive. That tells me we are decreasing, followed by increasing. And then we would find those values, find that value at 1. So let's do that over here. So f of 1 would be 1 minus 1 to the 4/5 plus 3. And this is what we did at the top. This is still 3. Based on the arrows, we have decreasing followed by increasing. That results in minimum. So we have a local min at x equals 1 and y equals 3. And that point is 1, 3. If it's asking for the minimum value is 3. Okay. 9, we want to find the extrema of f of x is equal to 8 natural log x minus x squared. So first, let's find the derivative. So what is the derivative of 8 natural log of x? 8 over x minus, what's the derivative of x squared? That's 2x. Okay. All right. So first we want to find where f prime of x is equal to 0. So I'm going to set 8 over x minus 2x equal to 0. And I'm going to solve this by moving the 2x to the right side. And then cross multiply. So the x goes to the right side. And we get 8 is equal to 2x squared. Next, divide by 2. And we get 4 is equal to x squared. And then you could either factor, or you can just take square roots and remember to use plus or minus. This would be plus or minus 2. Now, the original domain of this function is based on the domain of the natural log. Natural log has a domain that starts at 0 and goes to infinity, but it does not include 0. Okay? You cannot take the natural log of 0 or anything negative. So which one of these numbers fails to be in the domain? Yeah. Yeah. So really, we just need x is equal to 2. We had to get rid of x equals negative 2 because it was not in the domain of the original function. Okay? So think about the definition of critical value. It has to be where f prime is 0, but it had to have been in the original domain to start with. Negative 2 was not, so it's out. Okay? The other value that we need to worry about comes from this 8 over x. What value of x makes 8 over x undefined? 0. So x is equal to 0, but 0 is, again, not in the original domain, so we don't have to worry about it at all. So we do not end up with another critical value. We just end up with a critical value of 2. So let's draw up the points here. We have one critical value at 2. We have intervals. We have f prime. And we have f. Now be very careful when you draw up your intervals. Your intervals are based on the domain of the function. So instead of starting at negative infinity, it starts at 0. And goes 0 to 2, 2 to infinity. Then I need to test the derivative. I'll test it at 1. So 8 over 1 minus 2 times 1 is 6, so that's a positive. And then I need to test it maybe at 3. Now I'll tell you what, I'll test it at 4. Yeah, this will work out good. Test this at 4. So 8 over 4 minus 2 times 4 is 2 minus 8, which is negative. And that ends up with increasing followed by decreasing. So this results in a local max. We would need to find the value at 2. So f of 2 would be 8 natural log of 2 minus 2 squared. Depending on what we're doing with this, would determine whether or not we leave it in this form or get the decimal approximation. If you are working a word problem, then go ahead and get the decimal approximation. Otherwise, leave it just like this. And then that's what we would say. So we have a max, local max, at 2, 8 ln 2 minus 4.